Okay, so good afternoon. Let's start our pre-party session. So the next speaker is Nikolai Bobenko from Geneva. He will talk about dimmers and M-curves, limit shapes from Riemann surfaces.
Thank you very much. So welcome to my talk. I want to take you on a little bit of a journey into the world of dimers. And thank you for the organizers for the invitation and the opportunity. So from what I understand, this crowd is not super familiar with dimers themselves. I'm going to give a little bit of a basic introduction as well, and then present some new results. So I should say this is based on two papers, one called Dimers and M-curves, and then a follow-up about actual limit shapes. So done with Sasha Bobenko, myself, and Suris, and it's all very recent work. So, okay, what are we talking about? So the dimer model itself, we have a graph, let's say a finite graph. We will be restricting ourselves to the case of bipartite and planar graphs. Here's an example. And then what we care about are what we call dimer configurations, which are just perfect matchings. So if you look at the dual picture to that, and we will actually just be working with the square grid, what this looks like is something like this, right? So it's a domino tiling of a domain like this, right? So this is one example of a dimer configuration that we have right here. There we go. It's one example of a dimer configuration, but what we want to do is take a random one, right? If you do that, if you take a random one, your picture is going to look like this. And it turns out that there's kind of a limiting behavior happening here. So basically with probability 1, my picture is going to look like this, right? So you always have kind of a circle phenomenon occurring if you take a random one. So here, when I say random, I mean out of all the possible dimer configurations, I uniformly pick one at random, right? Yes. So this particular graph that I'm talking about here is called the it's called the Aztec diamond, and well, maybe I should say what the colors indicate. So when you have a square grid and you have and you tile that with dominoes, you have 4 different types of domino tiles. I'm not sure if this is this visible? Visible enough? Okay. So you have 2 different kinds of vertical dominoes, one with black on top and one with black on bottom. So this is 2 different types of vertical ones, and you also have 2 types of horizontal dominoes, depending on where the black or white square is. Right, so the colors here indicate just what kind of domino that is. So all the dominoes here are vertical, all the dominoes here are vertical, but they're of 2 different types, right? So I'll just zoom in a little bit once again to kind of show you what this kind of looks like. You see, indeed, here we have a frozen region, and the behavior here looks more chaotic, but also clearly the behavior on this right side, inside of this chaotic region, and on the left side is different, because here you have lots of dark blue ones, and here you have lots of light blue ones, right? So, and kind of the goal here is to describe this kind of limiting behavior. Okay, so I should say that kind of in bijection to these kinds of dimer configurations, there is a height function, and if we want to talk, so this is purely defined on a combinatorial level, something like whenever you step over a dimer, you add +1 or -1, and so this is in bijection, so really we want to study this height function, and there is a limiting statement here saying that if you take this limit and make your grid size smaller and smaller, and this is a result from 2001 by Cone Canyon Prop, that indeed this height function should converge to something that is a minimizer of a kind of surface tension integral. So the surface tension here, the surface tension is a function that depends only on the slope of your function locally, and you can think of that as a kind of entropy, as a local entropy. Right, so one could think that you can just solve the corresponding Euler-Lagrange equation, but it turns out that this, the difficulty in that is that the sigma here, it has some non-differentiabilities, it has some singularities, so yeah, that makes it, you need the appropriate kind of generalizations for this Euler-Lagrange equation to make sense. Yes, okay. So maybe I should comment a little bit on how this kind of picture is produced. A nice way to think about that is the following. I'll just show you an animation and you'll see what it means. So here I start with this kind of frozen configuration that I had at first, and then I run a Markov chain, and you see that, okay, no, this doesn't work. Very sorry about that. Okay. Okay, I was doing this on my own computer and there it worked, but I'm not sure how to open the GIFs here. Huh? Sorry? All right, let's try that. Where was that? Nope. Okay, this looks good actually. Very nice. Okay, so what we see here, it's a Markov chain running, so it should start over in a second. Yeah, so we start from this frozen configuration and we start doing kind of local flips. And you see that it kind of converges to this uniform, well, this is a Markov chain that should converge to the uniform, to a uniform sample. And indeed, we see that kind of this circle shape emerges very naturally here. And really, all that I'm doing here is I start with whenever I have this kind of local configuration, I can just flip those two to this without disturbing any of the global picture. And basically, this is what is being done here as a Markov chain. Right. All right. So, okay, so this was all in kind of the uniform picture for now. You can add weights, and the natural way to add weights is you put weights on the edges, and then the probability of a dimer configuration is just the product of all the weights on the edges that were included. And then other behavior can emerge. So what we have here is, in this example right here, we have doubly periodic weights, meaning you have some small fundamental domain, and you keep repeating the same weights on the entire graph. And, well, we see that the behavior is all of a sudden kind of a third kind of phase has emerged. So here we have still the frozen regions that we saw before. We have this large region right here that we call the liquid region, but a new phase has emerged right here, which is kind of a flat piece like this. Or if we talk about this in terms of the height function, it's a flat piece. And these are usually then called gas bubbles, right? So we have three phases, liquid, frozen, and gas. Right, so this is kind of mysterious, and this was studied by Kenyon, Okunkov, and Sheffield in 2007 with very elegant kind of, yeah, I guess building the connection between these dimer models and algebraic geometry in a very elegant way. So it turns out if you take this is a picture of the fundamental domain. I have weights on all the edges, and then you take the adjacency matrix and you kind of alter it a little bit. So this is, you consider the adjacency matrix on a torus, and this defines you a spectral curve if you take this determinant of the altered adjacency matrix. And then from this spectral curve, you can define, well, you can study the limiting behavior of the Atzig diamond just through the spectral curve. Right, but still, it turns out it's still kind of hard to say what the actual minimizer looks like. And kind of the point of our work is actually an inverse type problem. So we do not start with doubly periodic weights. What we start with is a Riemann surface, which is this picture right here. I'll explain in what sense this is a Riemann surface, but this is actually the picture of the actual Riemann surface that we work with. So we have a Riemann surface. In this case, it's a Riemann surface of genus 2, as well as a few chosen points on one of its, well, a few chosen points on that Riemann surface. This defines you both the weights of the dimer model, but also it turns out that this Riemann surface that we start with is then the spectral curve that can be used to compute, for example, the limit shape. So in this picture here, this is a hexagon, so slightly different graph. I'll zoom in just so you see what it looks like. So we're not doing dominoes, but lozenge tilings. So in this picture, this is a large hexagon. It's populated with weights coming from just this data right here. So this Riemann surface on the right is used for two things. It populates our graph with weights. So then I do a simulation and I get this colorful picture underneath. But also you can use this data to compute the limit shape. And this is used, for example, to draw these white lines that I have here. So this white curve right here is a prediction of where the phases should separate. And we see that it matches quite nicely. So, and as I'm saying, I didn't draw this by hand. This is like actual computation just based on this data. Right? All right. Yes, please. Yes, this is, yeah, absolutely. All right. So in fact, you will later see that there is a diffeomorphism between this region and this liquid region, right? So yes. All right. So let me start a little bit with the setup. So as I said, I need to explain a few things in the setup. I need to explain how the weights are defined, right? So again, we start with this as data, right? This is a Riemann surface in some sense, which I'll explain in a little bit. I start with this data. I want to define the weights from that, and then I also want to basically explain what this diffeomorphism is, right? All right. So yes. So something that I've not really told you about yet is that actually it makes sense to consider complex weights on all the edges. They don't have to be real numbers, or rather positive numbers. They can be complex numbers, and they define a dimer model. Well, or actually, let me put it this way. So you have weights on all the edges, but this specifies your dimer model because you can scale all the edges around one vertex with the same. There's gauge transformation, and this does not alter your actual measure, right? So the actual physical weights in this case are what's called the face weights. These are cross ratios of all your edge weights around one face. And it turns out that complex edge weights define you a dimer model if and only if this Castellane condition is satisfied. So these face weights, they need to be, first of all, real, but also they need to be of the correct sign, right? And this, yeah, goes back to Castellane. I didn't put a year here. I'm very sorry. Okay, so now this is kind of the combinatorial setup that we'll be working with. The dimer graph lives on the black and white, so on the black edges. So a dimer configuration is a subset of the black edges. And then, well, we introduce what we call the quad graph, which is both the dual graph and the original graph. And you draw these quads around them, and then there's these train tracks that run from the one side to the opposite side of the quad, right? And attached to each one of those, there will be a parameter, which is just a point on the Riemann surface. All right. So this is what this kind of configuration looks like around one vertex. So the data that we have, again, is we have a compact Riemann surface of some genus, and we have parameters which are just points that lie on that Riemann surface somewhere, which I call alpha I, right? So now it was work done by Fock in 2015 to introduce these weights that turn out to be the right inverse weights. And well, it's basically how you introduce those is based on Baker-Accuser functions, which I'll skip. But in the end, you end up with weights on all the edges, and those are exactly the right weights that have the right spectral properties. All right, so in the end, what you get are some complex weights. They were introduced, as I said, by Fock in 2015. But complex weights is not enough for us. We want to introduce dimer weights. And dimer weights, as I said, they need this Castellane condition, which is a sign condition around a face. And it turns out that this is satisfied, essentially, if and only if you take a special kind of Riemann surface with special points chosen on it. Right? This Riemann surface has to be an M curve. An M curve I'll draw right here. So basically, when we draw a Riemann surface of, let's say, genus 2, usually we draw something like this, right? Something like this. So an M curve is a compact Riemann surface along with an anti-holomorphic involution. So, for example, I could have an anti-holomorphic involution that flips it from left to right, something like that. This involution has fixed points that are right here. These are the only fixed points of that involution. So this pair would not be an M curve because an M curve has an involution which fixes the maximal amount of connected components. So here we only have one connected component, but it needs to be G plus 1. Right? So instead of this, what I'll choose as my involution is a flip from top to bottom. And then the fixed points, or what we call the real ovals, are just right here, here, as well as here, right? I hope that's clear. Okay, so these real ovals, they separate my curve into a top and a bottom half, and then I can apply a generalized Riemann mapping. So I'll call it the Riemann mapping theorem, but it's a generalized Riemann mapping theorem, which maps this to the unit disk with two removed disks. Something like this, right? So this here, yeah. So this is exactly what you see in this picture, right? So in that sense, a picture like this actually encodes the entire complex structure of my Riemann surface, right? In fact, here just the z coordinate, so the plane coordinate here, is actually the conformal coordinate of my Riemann surface. But it's convenient because in this model right here, you can actually do computational stuff, and we'll come to that later. Right, okay, so this is an M curve. And, well, it turns out that if I choose all of my parameters just on, let's say, on x0, right? If I just choose them somewhere here, then this, basically this anti-holomorphic involution, it just guarantees that all my face weights are going to be real. Right, but we need more than real. We also need that there's a sign condition that is satisfied. And this was studied in great detail in Boutelier, Massoni, and Detellier in, 4 and 3 years ago. And they show that basically it's a kind of clustering condition that needs to be satisfied by the angles, by these parameters that we have chosen. And then we get this, this is exactly then the case where our complex weights define us an actual dimer model. Okay, so let's, I'm being very vague here, just some kind of ordering or clustering condition. Let's make this a little bit more concrete. We're working with a square grid, right? So again, the black graph right here is, it's the square grid where the dimers live, and I've drawn the train tracks as well. So there's 4 different kinds of train tracks. There is 2 verticals, they point in 2 different directions, and 2 horizontals, again, they point in 2 different directions. I denote the parameters corresponding to them as, alpha plus, alpha minus, and beta plus, beta minus. And then this ordering or clustering condition that needs to be satisfied is basically exactly this. So we know that the sign condition, we know that this data defines us a dimer configuration if and only if this clustering condition here is satisfied. Right? So all the alpha pluses need to, the kind of the clusters cannot intersect. Right. So then similarly, you can do the same thing on the hexagonal grid, and then again this Castellane condition is still just a clustering condition, but with 3 clusters. Right. Okay, so I should say, so now our setup is actually the following. We take the square grid and we doubly periodically keep repeating these train tracks, the parameters, right? So the next one here would be again alpha 1 minus. This does not necessarily mean that the weights that, I was very vague about the weights, but these phase weights, they're not going to be periodic just from that. They're going to be quasi-periodic. Basically, so this is a result of computation. This is a genus 1 and a genus 2 picture. And the phase weights are kind of a lattice superimposed on these pictures. But the period of the lattice and the period of these pictures doesn't have to match up, and so we get quasi-periodicity instead of periodicity. Okay, so it is clear which condition leads to doubly periodic weights in this setup. And it is just, Abel-Jacobi type of condition. And in fact, this kind of setup, even though, it seems very kind of complicated and, there's a bunch of theta functions involved, but really it covers all the doubly periodic cases. And all it does is it relaxes this condition right here, because whenever you work with doubly periodic weights, you're just implicitly carrying a condition on your choice of parameters, which is not an open condition. So, yeah. So if I start with doubly periodic weights and just alter my parameters a little bit, I'm not going to stay in the doubly periodic setup. Yes. All right. So are there any questions so far? Okay, I'm going to move on now to, so this was the kind of the definition and some properties of the weights. Now, what we want to do is, again, we start with this data that we use to define the weights, but we want to define the algebra geometric objects that are then used to do kind of predictions of the dimer model. So, okay, we start again with this kind of data. It's an M-curve along with chosen parameters that fulfill this clustering condition. So then what is being kind of the principal objects here are these two differentials. So they're normalized meromorphic differentials, meaning they have purely imaginary periods. And I'm going to choose d zeta 1 to have plus or minus 1 residue at the alphas and d zeta 2 at the betas. So this, yeah, this kind of corresponds to this kind of corresponds to periods in the two fundamental directions of my, yes, please.
So what's the normalization? Is it real normalized or normalized?
Sorry?
What's the normalization for the differentials? Is it
It's
normalized?
purely imaginary periods.
Okay, because you have 0 A periods.
Yes, and 0 A periods, yes. Well, yeah. Okay, so then if you take the integral of those, if you now take the integral of those differentials, I'll call their real and imaginary parts x and y. This is then well defined on R plus because we have 0 A cycles. So my A cycles are just these. And then it was shown by Ketchever in 2014 that actually just the map from R plus to the x's and the y's are diffeomorphisms, right? So you can look at those those as coordinates. And here's a picture right here. So, yeah, again, we start with this, and this is typically, especially in this is typically called the amoeba map. So this is a generalized kind of amoeba map because we're not in the algebraic setup. And so we see that all of our chosen points, they're mapped to infinity. And both of our holes, they're mapped to holes in the amoeba as well. And this kind of clustering condition that guaranteed that our weights are real, in this setup, it guarantees that there's no intersection of these infinite tentacles. So that's why this is actually a diffeomorphism, right? So then furthermore here, this is typically, in the algebraic setup, this is known as the Newton polygon. But this is a generalized version. So in the Newton polygon, all the marked points are always integer points. Here, this is a generalized version of that. These two marked points that correspond to the holes that we have here, they don't have to be integer points anymore. Right, okay, so now we have these two maps. So then, furthermore, and this is actually a new result, this kind of representation of these, we introduce the Ronkin function and the surface tension. So this right here is the Ronkin function. It doesn't really matter what the formula is, but it is, it's a formula in terms of all the objects that we've already seen. And we have this sigma right here, which will play the role of the surface tension, which the dimer height function minimizes. So it turns out that these two functions here are Legendre dual, which you can see just from the definition. They're Legendre dual, and well, all these definitions agree with the doubly periodic algebraic definitions. So then, going back to my zoo of objects, I've added these two arrows right here. So it turns out that if I take the gradient of sigma, so sigma is a function with its domain being the Newton polygon and going to R. If I take its gradient, I go into the amoeba, so it's just the composition of these two maps, right? And the same in the other direction. All right. So now, yeah, so as I said already, it was shown that the height function in general converges to the minimizer of this surface tension integral. For doubly periodic weights, this was shown, well, a while ago. And so now, in our first paper, we showed that this is still true for doubly periodic weights. And, well, now kind of the question is still, what does this look like? So let's just stick with the example of the Atzig diamond. This was done in complete generality for the Atzig diamond for doubly periodic weights in Becken and Borodin in 2023. But the thing is, their proof relies on a bunch of kind of heavy machinery, a bunch of integrability properties, which are not necessarily hopefully needed because we just have this kind of generalized Euler-Lagrange equation in this setup. So yeah, this is exactly the point of our second paper, that purely variational proofs are possible. And this hopefully can then be extended to other kinds of domains. Right. Okay. So now, in Kenyon-Okounkov, basically what was shown is there was an introduction of a very natural complex structure on the actual liquid domain of the dimer. Right, so now we're, we're thinking we're on the Atzig diamond. There's the liquid domain, and you want to map between that and your spectral curve somehow. So this map was, at least in this form, introduced in Beck and Borodin, and this is where we take this from. So you define a family of differentials, which I'll call d zeta. And they're just given by this kind of, linear combination of d zeta 1, d zeta 2, and now there's a third term, d zeta 3. So d zeta 3, is just given by these residues. It doesn't really matter. In some way, it gives you the boundary conditions that correspond to the at-stick diamond. So you have a family of these. So for each point uv, and uv here is going to live on the dimer domain. This is the point on the dimer domain. So now, okay, we can count the number of zeros, which is just this, right? And, well, now the point is that if our uv lives inside of the unit square, then, well, first of all, there need to be 2 zeros on any inner oval, just because of this real condition, and then also 1 0 between any parameters of the same type. So if you kind of count that, you will see that this leaves us with exactly 2 free zeros. And now the definition of the map between our curve and the dimer region is then exactly this. So if we have a UV that has where this free zero right here does not live on the real ovals, but rather is self-conjugated, then we call this UV part of the liquid region. Right, and in fact, this defines your map in a kind of convoluted way, but this defines your map between this upper half of the Riemann surface and the dimer domain. And then it was shown, again, in Beck and Borodin, that this is in fact a diffeomorphism. Right, so let me draw that for you. It looks like this. Right, so again, I choose a point on my Riemann surface that does not lie on the real ovals. I choose a point here, and then it turns out that there is a UV here whose corresponding differential has that as a 0. Right? That's the definition of this map right here. All right, but just in general, sorry. In general, this is what your picture is going to look like. So your inner ovals, they get mapped to gas bubbles with exactly 4 cusps. All the marked points that we have, they get mapped to points, to tangential points of the boundary of the dimer, and yeah, and also your orientation is reversed. But basically, this is always what your picture is going to look like. All right. So now, how much time do I have? I have 20 minutes still?
18.
18, okay.
Right.
Okay. So I should probably say this then. So it turns out that if you, okay. Yeah, so it turns out that if you now take so again, the x coordinates are the ones living on the amoeba, the u and v coordinates are the ones living on my at-stick diamond. So it turns out that if I take the divergence with respect to uv of x1 and x2, as well as with in the Newton polygon, these are divergence-free fields. So, whenever you see something that is divergence-free, you want to integrate that. And yes, so let's ignore that. Actually, if we integrate those, sorry, I'll just go here. So if we integrate those, this will define us what we call now the complex height function. So this is just the integral of these. Okay, so the complex height function at a point uv is defined as the integral from somewhere, from some fixed point to the point p, which corresponds to the uv, and d zeta uv. So here, this is not a meromorphic function actually, because there's a subtle, the p and the uv are not independent, right? So in that sense, this is not actually meromorphic, but this defines as the complex height function. And then denoting the real part and the imaginary part as h, we see that these functions are exactly the integrals of these x and s fields that we saw. So this is nice. And in fact, it turns out that H then can be finally extended to all the holes. And it turns out that this extended version then, so this is now really a function defined on the entire acidic diamond, is in fact the minimizer of this surface tension function. And the surface tension is a convex function, so it's clear that this is unique. So this is indeed the function that we're looking for. Furthermore, actually, this G that we introduced here is what we now call the magnetic tension minimizer. It minimizes the very same functional, but with the Ronkin function instead of the surface tension. So this is still kind of a mystery to me. Actually, this is not very well studied. Like everyone studies this H in this dimer world, but it's not clear if there is a good, a good probabilistic interpretation of what this G actually is on a discrete level, maybe. So it's clear that H is the height function, and the height function converges to that, but there's kind of a question of what is it that converges to G? Maybe there's something there. But, well. Okay, but going back to our favorite picture, what we see is I have added another two arrows right here, this one and this. So it turns out that the gradient of H just goes here, the gradient of G just goes to the amoeba. And in some sense, this is kind of an extension of the Legendre duality that we have between the amoeba and here. We extend that to the liquid region of the dimer. All right. So now, again, so here this is actually now exactly this example, right? So this is using exactly this data to get a configuration right here. As I said, everything that I'm showing can be computed completely explicitly. There are formulas for, well, the weights are computed in terms of theta functions. That can be done, but also these curves that we have right here, they can be computed quite nicely if you start with a uniformization like this. So this kind of inverse approach here, in some sense, it gives you, this is what enables us to do this computation, because if you just start with some algebraic curve, first of all, it's very hard to compute, for example, the B matrix which you need for theta functions. It's not clear, and also not clear how to compute any of, well, the differentials are also hard to compute and things like this. So this nice uniformization is what allows us to do this. So there's a technique, you can interpret this picture here as a Schottky uniformization, and then you can write some converging series over some group, and this gives you this picture. All right. Proof idea. Maybe I'll skip that. So basically, you need to, as I said, the sigma here, it has singularities at all the marked points, like the ones for all the bubbles. There's a conical singularity there, and this is what makes this challenging. So you need to generalize that in some sense. So we already saw that this one here is divergence free, and this is exactly actually, this corresponds to exactly this Euler-Lagrange equation. So just by construction on the liquid region, our Euler-Lagrange equation is satisfied. But you need to extend that to all the frozen and to the gas regions. And here kind of the difficulty is you need to do that in an appropriate way, because those are exactly the singularities of sigma. Well, and since our function is convex, you can do that in terms of subgradients. And then it turns out that this is kind of nice. So this was studied right here in 2020, but only for the genus 0 case, meaning that there are no gas bubbles, but only some frozen regions. And there, this extension can be done, and we kind of use a similar idea as they do, but we're able to extend that also to the gas regions. All right. Okay, so maybe I'll just say a few words about the hexagonal case. So what is now different about the hexagonal case? So if you, let me just draw something maybe. So we had the simplest case of the at-stick diamond, and you have a frozen region here. You have all the different frozen regions, and all four of them are actually different. Right? All four of them are different, and they correspond to the four corner points of your Newton polygon. Now, if we look at the hexagon, in the uniform case, let's say. So, simplest example, you have a frozen region here and a frozen region here, but they're actually of the same color, right? So these are the same kinds of frozen regions, and so you should not expect to have a one-to-one map from your Riemann surface to here, because both this and this should correspond to the same point on the Riemann surface. But it turns out that indeed there is basically a 2-to-1 map going to the hexagonal region. And then if you consider more complicated regions, you should have some kind of complicated covering structure or something like that. This is an unsolved problem in the very general case, right? But in the case of the hexagon, we were able to solve this just because there's this kind of symmetry and the region is nice, and so you can make an educated guess of what the solution should be. All right, so basically, as I said, we exploit the symmetry of the hexagon by just choosing a kind of symmetric uniformization like this. So here I have a symmetric uniformization which respects just the z minus z symmetry. But I should say I call this r hat. This is a double cover of my spectral curve r. So the weights are defined on this r right here. So the weights that correspond to this are genus 1 weights, right? But yes. But so then you do the exact same thing. You still look at this family of differentials right here. Well, you have to choose this d zeta 3 in the appropriate way. But now d zeta 3 lives on this double cover, right? D zeta 1 and d zeta 2, they are symmetric, so they actually can be extended to just R. So they are still defined on R, which is how it should be. And so then, yeah, again, you define this family, you count the number of free zeros, it turns out, again, there's exactly 2. And this, again, defines you the map between this double cover and the liquid region of the dimer on the hexagon. Same exact game. You still have all the same properties. Again, your height function, or like this h, can again be extended. It satisfies the hexagon boundary conditions, and it turns out again that this is the surface tension minimizer, but now on the hexagon. So again, we look at our favorite picture, and this is now slightly more general again. We still have all the things we had before, but now there's an extra step here, which is exactly this double cover that I mentioned. So this R plus right here is the actual spectral curve where their weights are defined. The maps to the amoeba and the Newton polygon go from just R plus, right? But then there's this double cover, which is R hat. We chose this to be, we chose the symmetric uniformization for that. And there is a diffeomorphism, again, going from this to the liquid region right here. And yeah, as I said, you can play all the same games. You still have these right here, but now this is, of course, a 2-to-1 map. All right. Oh yeah. So actually, are there any more questions? Yes. Yeah, what's the question? So, yes, well, if you have, you start with this Schottky uniformization right here, you can compute the B matrix from that. That allows you to then compute the theta functions that are involved. So, I mean, to compute theta functions, you just need the B matrix, right?
You mentioned short-key information. What
Yes.
do you mean by using the short-key information? Why use short-key information? What are the advantages, please?
Because then everything, all the objects that we have can be computed as converging series, and the series are just sums over the Schottky group. Yeah. And essentially the formulas are, so if we just look at the genus 0 case, then all these, again, all these formulas can just be expressed through rational functions. And, well, in the non-genus 0 case, you have basically the same rational functions, but you have to kind of average them over some Schottky group. Yeah. Okay, so let me just conclude with a little gallery. So here's, for example, one thing that you can now do is you start with this kind of picture, and now you can do this kind of evolution right here. So what I'm doing here is really just changing one parameter, which is the size of the hole, right? And you see that still it matches very nicely, and indeed you get this kind of flat piece and this gas bubble behavior right here. So then these are two genus 0 examples, in which case, as I said, everything is just expressed in rational functions. Yeah, maybe I should zoom in on this for a second. So this is kind of curious. So here we had this frozen region, which is just a brick layer pattern, right? And then here you get a different kind of frozen region, which is still a brick layer pattern, but now has two red ones and one blue one. Then here you have this one, two blue ones and one red, and then that transitions to completely blue, right? I think that's pretty curious. And similarly here also you have a similar kind of thing. This is also, it's a large frozen region, but it's a mix of the two different colors, right? All right. And then the same technique can also be applied. Okay, I'm not sure what's happening here. The same technique can be also applied to hexagons that are a little bit skewed, like this. But, you know, it's basically the same thing. You just have to alter the residues of d zeta 3 a little bit. This right here is, yes, so this is a genus 2 example, but so it's our hat that is genus 2, but the weights that correspond to this are genus 1. Right, so this is already the double cover of the spectral curve. Yeah. And then, yeah, I conclude. Thank you.
Thank you. Do you have questions?
Is it possible, and is anything known about the case when we have infinite number of parameters, but they still have this clustering property?
Yeah, it's a very good question. Yeah, so it would probably be a pretty natural setup to, instead of choosing like 3 points or something, you choose a measure or something like that. I don't know about that, yeah. So it's a good question, but I don't know.
Also questions?
Maybe it is a similar question as the previous question. Just so in the beginning we define the weight by the edges, right?
Yes.
But when we consider the curve and genus and singularities and consider this picture with liquid region and gas region, so can we recover the weight? I mean, like you have a weight on probability. It's just like you can got this picture by a Markov chain with a transition matrix with weight, right?
Sure.
And so can we recover the weight from the settings by algebraic curve?
Well, I mean, in some sense, this is what we're doing. Like, in some sense, you know, I'm able to design a picture like this, right? Like, I come up with a form that I want to get, and then I choose my parameters in a way that this is the form that I get. So in some sense, this is exactly what we're doing.
Yes. Then can we have something like there is just like what he said, there's a measure with weight with probability, then give it an automatic process, then the dimer model will change. become with the station distribution becomes this.
Yeah, maybe. So yeah, maybe.
In real life, there are dimers in monomers with defects, you know, right? There will be
Sure.
no M curves, I'm afraid, in real
Absolutely,
life.
yes, of course.
Yeah, so agree, right? So
Yes.
we can see really M curves, which is like like this, right? Okay, thank you.
Yeah. Yeah, I mean, this is very special to just dimers, yeah, of course.
Yeah, is there a conceptual reason why the existence of these conjugate zeros corresponds to being in the liquid region?
Yeah, I don't really know that. So, in some sense, it's some kind of projective duality in the end, like a kind of generalized projective duality. I don't have a conceptual reason for that yet.
And I guess how did you discover it? Because it seems like some miraculous.
Well, I mean, we basically took it from the Borodin paper. They arrived at this formulas from, you know, crazy complicated computation, essentially, right? But still, I don't, like, also in their paper, I don't see a conceptual reason for it.
Right.
Yeah. Mm-hmm.
Thanks.
Yeah.
Okay, maybe one more short question.
You've mentioned now several times that the initial part with that stacked diamond and set comes from the Borodin's paper with some complicated machinery.
Yeah.
Maybe you can mention, like, say some words about what this complicated machinery was.
Yes, so they do a lot more than just compute the limit shape. In fact, you know, you can look at the next level of approximation, which is the fluctuations of the height function, right? Or like local statistics of your dimer model. And for that, you need to compute the inverse Castellane matrix, or the inverse matrix, right? And yeah, they use, you know, integrability of some commutation of 2x2 matrices, something like that. But yeah, so as a result, they get some, they get more than just the limit shape. They get some kind of local statistics as well. But yeah, the point of this work is just in order to just compute the limit or prove that this is the limit shape, you don't need that. Yeah. Mm-hmm.
Okay, let's speak again.
Thank you.